All right, so the machine that we built last video it turns out it can't separate this pattern because geometrically what our machine's able to do, the expressive capability of our machine is just drawing straight lines. And this pattern XOR, let me remind you, this pattern is called XOR. It's not linearly separable. That basically means we can't distinguish it with a single line, right? So we're going to have to make some adjustments to how our machine works to be able to give it the expressive capability to solve XOR. Now, how do we do that? Let's start off by formalizing XOR a little bit. So remember, each of these points is essentially like a coordinate. And I'm just going to write these out. Each point, XY coordinate, we have both positive ones, both negative ones, and then we have these mixed pairs. So that's kind of how we can distinguish XOR. Let's assign a different color to positive one and negative one to kind of illustrate this relationship. So let's say, for example, all the negative ones are pink, right? And all the positive ones are blue. XOR is going to fundamentally fall into two categories. It's asking, how do we distinguish the mixed pairs? So essentially like pink and blue from the matching pairs, which would be like pink, pink, or blue, blue. Pretty straightforward. And essentially what we want our machine to be able to do is to distinguish these mixed pairs from matching pairs, have the expressive capability at least to do so. What we were doing in the last video was using the sign of the output score of our machine, which was either positive or negative, remember, to distinguish a score. And that's kind of how we would categorize our points. And that would work for a simple example where we're able to draw a straight line to kind of separate these categories. But when it comes to separating these mixed and matching pairs in this coordinate system, we're going to need more expressive capability than a single straight line. This is our machine up here, right? This is kind of like an illustration of our machine. So the first thing you might think is, what if we get two of these machines and kind of get them to interpret the input separately and then combine their scores? So let's try that out. So let's say we have our first machine, machine 1, and that's going to have the same setup we looked at, right? 2 weights and 1 bias. Can label these bias, weight 1, weight 2. And we'll make a second machine that has the exact same setup. And remember, we have two possible inputs, right? Input 1 and input 2. And so each of these input pairs, what if we feed each of these input pairs into each machine separately? And then once the machines are done evaluating the input, each machine spits out a score, right? And imagine that score then gets combined into an output. Now, what do you think would happen if we did this? So we feed in an input, each machine still represented by the same formula we looked at earlier, the first weight times the first input, second weight times the second input, and the bias, spits out a score. Like inside each of these machines, we can still interpret, imagine this is like a sort of thinking bubble, just imagining what's going on inside the machine. We could still imagine like a linear boundary being drawn somehow, right? And on one side, all the numbers are positive. On the other side, all the numbers are negative. And on the line, all the scores are 0. All right, and let's imagine the other machine has different weights and bias and is essentially drawing a different boundary and scoring the same inputs differently. So boundary might be arranged like that. And one side, all the points are scored positively. And on the other side, all the points are scored negatively. Now, if we were to naively just combine these, we can imagine the final score is equal to the score of the first machine plus the score of the second machine for any given input point. Now, if we were to kind of do this, what we would get is just another linear boundary. In this case, with this particular arrangement of weights, the linear boundary we'd get would be something like this, where on one side, all the points are negative. On the other side, all the points are positive. And again, the linear boundary is all the input points where the score is equal to 0. Fundamentally, just naively combining two of these machines has not given us more expressive capability. We just get another linear boundary that is kind of like where these two machines cancel each other out. So wherever this boundary is drawn is where these two machines perfectly cancel each other out, making the score equal to 0. But how do we use this idea of combining our machines to actually get expressive capability? We can start to think of this whole section right here that's in between the input and the output as a layer. So this is essentially a layer of our network. And this one particularly, we can think of as a hidden layer. We call it hidden because it is between the input and the final output. So a layer, it's essentially stacking these different machines on top of each other, right? But what are we missing? I would like to introduce activation functions. Activation functions. Now, you may have already heard of functions. I'm sure you're familiar with the classic f of x. And a function is essentially where you plug in some value and some rule gets applied to that value and you get a new value. So you plug in some input, you get some output. Now, an activation function is essentially just a role that a function can play. So technically any function can play this role, but we're going to want to use functions that behave in a particular way that's helpful as our activation functions to be able to give our setup more expressive capability. So the function I'd like to look at for this video is called the step function. And the step function is what we call a piecewise function, which is essentially just a fancy way of saying it has different rules applied to different parts of the input domain. So we're going to just write step to kind of denote the step function. And so let's imagine the step function takes in a number. In our case, it's going to be the score, right? Based on that number, the function can give us two possible answers, either 1 or 0. Very simple. If the score, or whatever input we put into the step function, in our case, it's the score, is greater than or equal to 0, then it's going to give us 1. On the other hand, if our input score to our function is lesser than 0, then we're going to get 0. So you can imagine, if we were to plug in 0.01, that would technically be lesser than 0. So the activated score, we can say, in that case, would just be 0. If we were to plug in, say, 2,000, that score is greater than or equal to 0. So it would simply just return 1. All right, so let's imagine we're taking the score from each of these machines. What this would give us is something we can denote as an activated score. Sorry for the messy diagram right here, but hopefully it's getting the point across. So previously, the decision space was continuous. So at every point, our machine would score the input differently. At every input point, it would be scored differently. Now, once we apply the step function, the decision plane looks more like a discrete plane. It's less of a gradient and more of just two separate regions. To make this concrete, let's think back to an example. Say we fed our machine any input point. Previously, it might have scored it. It would have scored it as a unique continuous value. So it might have been something like minus 0.24. Just a random example. Now, when we feed that score into our step function, we get a discrete value. It's either 0 or 1. So in this case, when fed into our step function, we just get 0, right? So essentially what it's doing to the whole decision space is turning it into two discrete regions, right? 0 and 1. And remember, this is being done to both, right? So we can think of this as discretizing, for lack of a better term, both machines' decision space. And what that does when we go to combine these is it actually stops each machine from canceling each other out, and each machine is able to make a decision, a discrete decision on each input point. What it's going to do to this output plane is it's going to combine these regions. So let's draw like the first decision plane from machine 1 over here in this example. It's a little something like this, right? Sorry for the bad drawing. And then let's overlay this second decision plane from machine 2 on top of this to kind of illustrate the new expressive capability we have. So now in this combined plane, we kind of have different distinct regions where the score is different in each region. It's not continuously changing as it moves across the region. So like, for example, in this region, the score is 1. In this region, the score is 1. In this region, the score is 0. In this region, the score is 2. Now, this is really powerful because we can adjust the weights and bias of each machine and kind of move these now discrete boundaries around, and we can have a total of like essentially more categories than we did before, even though we're working with a lot less values, because now we can have like a total of 3 different categories. We can have regions that are 1, regions that are 0, and regions that are 2. Now, how do we use this to solve XOR? Let's talk about encoding the pattern. Earlier in the first video, the way in which we encoded the XOR pattern was with positive and negative scores. So essentially, we were looking at the sign of the score to tell us how our machine categorized whatever input point we care about. The positive and negative sign of the score we were looking at to categorize these points was just a way of interpreting sort of like an encoding of the XOR pattern. But now that it's not outputting just positive and negative values, it's outputting 1, 2, or 0, we have to kind of switch up the encoding. Like we can say we want the mixed input pairs to be scored 0, and we want the matching input pairs to score 1. Now, we could use a different encoding. We could say we want mixed to be 2 and matching to be 1. We could say we want mixed to be 1 and matching to be 2. We could pick a lot of different encodings with just these 3 possible outputs, but the important thing is that for this setup, the encodings have to be adjacent. So it couldn't be 0 and 2, right? That just wouldn't work geometrically or mathematically with this setup. Let's just write the targets right next to the points we want to categorize. So remember, we want this one to be 0. We want this one to be 0 since they're both mixed, right? And for this target, we want this one to be 1 and this one to be 1 because these are both matching pairs. So in order to solve this, we would need each machine to have a decision plane that looks a little something like this. Now, when we go to combine these, our output plane would look something like this. And so it would have this region in the middle where any point we put in is scored 0. So these 2 mixed pairs are properly categorized. And we'd have these regions on the sides where in each of these regions, the score for all these points is 1, so matching pairs are also properly categorized according to our target. We have successfully, by just creating this one tiny little hidden layer and applying these activation functions, which are just, useful functions to kind of treat the score a certain way, and combining these, we have been able to give our machine that has now essentially become a network of machines the expressive capability to solve XOR. Now, this is amazing, and this is really useful, but so far we've kind of assumed that the weights and bias are just magically finding the solution, or we've been manually tuning them with our hands. So for the next video, I want to look at how do we get the weights and bias to learn and be trained to find the pattern by themselves, to solve the pattern by themselves, as opposed to us manually tuning them.